Hi everyone. So today I'll be talking about the evolution of Ceph, a distributed storage system. There are some hard-earned lessons in this evolution that will be useful to other distributed storage systems as well. So this is a joint work with Sage Weil and Mark Nelson from the Ceph team, and Michael Kochnik, Greg Ganger, and George Ambrosiadis, my colleagues from CMU. So a few words about Ceph. It started as a research project in 2004 at UC Santa Cruz. Today it's a widely used open source system with hundreds of contributors and thousands of users. At the core of Ceph is a distributed object store called Rados, which can scale horizontally on commodity hardware. And on top of Rados, Ceph provides S3 object store, remote block device, and distributed POSIX file system, all on the same cluster. So there are many other distributed storage systems like Ceph, but all of them have a similar high-level design that you see in the slide. There is the client side implemented as a kernel module or library. This allows the clients to transparently access the storage system. There's the storage backend implemented in the storage node that reply to client requests. And there's the metadata service, which tells the clients which nodes to talk to. Some systems eliminate the metadata service and use hash functions to map data directly to storage nodes, but that detail is irrelevant to my talk because I'll be focusing on the evolution of the storage backend that runs on the storage node. Storage backend is a crucial component that sits in the I/O path and plays a key role in the performance of the overall system. So when we examine storage backends of many distributed storage systems, we see that they all follow the same convention. The storage backend is implemented as a thin layer on top of a general purpose file system such as ext4 or XFS. This convention is not surprising because file systems implement most of the functionality expected from a storage backend such as block allocation, metadata management, or crash recovery. Therefore, building a backend on top of a general purpose file system appears to be a no-brainer at the beginning as opposed to building something, a custom backend from scratch. It's only when the developers start imposing backend-specific requirements, such as storing millions of data, millions of entries in a directory, they start hitting the design limitations of general-purpose file systems. So while many developers realize these limitations, they still continue to stick with the file system and work around these limitations because file systems provide good performance, they are stable, and they can be managed using standard tools. However, based on our conversations with many developers, the primary reason they stick with file systems is that building a custom backend is similar to building a custom new file system, and most current file systems have taken a decade to mature. So the Ceph team also followed this convention and built multiple storage backends on top of file systems. As a result, they went through what we jokingly call stages of storage backend grief. So this graph shows how long each backend was in development and how long it was the default production backend. The y-axis is the names of different storage backends, and the x-axis are the years. So the first backend, eBuffs, which ironically was not based on a file system, was abandoned in favor of file store backend running on Btrfs, exactly for the reasons described before, because Btrfs already implemented most of the needed features and some extra features not found in other systems, file systems, such as checksums and compression. From 2008 to 2015, it was multiple cycles of denial and anger stages as different file systems, Btrfs, ext4, ZFS, UFS, XFS were tried with unsatisfactory results. Then there was a short bargaining stage with the new store backend in which the team said, okay, we accept that file system metadata does not scale, but maybe we can use it just for storing data. The experience led to a brief depression stage, not shown here in the graph, and then to the acceptance stage, at which point the Ceph team completely abandoned file systems and developed the Blue Store backend. So BlueStore is a backend implemented from scratch in user space running on a raw disk. It is 2 times faster than file system-based backends on common workloads. Since BlueStore has a complete control of the I/O stack, it implements new features such as checksums, compression, erasure coding. These are the features that were hard to implement efficiently on top of a file system. So I guess it's not surprising to this audience that a custom backend performs better or implements features more efficiently, because databases have long realized the file system overhead, and some even bypass it. And exokernels have shown that low-level abstractions tailored to the application result in a significantly better performance compared to general-purpose OS abstractions. Perhaps what is surprising, though, is that unlike general-purpose file systems that take a decade to mature, the BlueStore backend stabilized in less than 2 years. To summarize, the Ceph project experience has the following takeaways. First, just like databases, storage backends are performance-critical pieces of code, and therefore they should bypass the file system. Second, implementing a backend with a small custom interface can mature much faster than implementing a full-blown POSIX file system. And third, with full control of the I/O stack, comes the freedom to quickly and efficiently adopt new and backward incompatible storage devices. Now I will talk about some of the challenges that general purpose file systems present for implementing efficient storage backends. So some distributed storage backends, including Cephs, have a transactional interface because transactions simplify the overall system design. But this is a challenge when building a backend on top of a POSIX, on top of a file system, because the POSIX, the interface supported by most file systems, does not have transactions. There's a large body of academic work that introduces transactions to file systems and operating systems, but still no production file system supports transactions. The Ceph team tried 3 common approaches to building transactions on top of file systems. One approach is to leverage the internal transaction mechanism of the file system. Such a mechanism exists in most file systems for ensuring their internal consistency, but it's usually not private. Another approach is to implement a write-ahead log in user space, and one other approach is to use a database with transactions. The Ceph team first tried to use butterfast internal transactions with the file store backend, but the lack of rollback mechanism led to inconsistent file system state in case of crash. And attempts to work around this using snapshots or introducing a new system call turned out to be too costly or complex. This led to implementing a user space write-ahead log file, which worked fine but had high overhead because, unlike file systems, the storage backend in Ceph cannot lose power in case of a power failure. Therefore, data had to be written twice, which halved the disk throughput. NewStore used RuxDB transactions and copy-on-write data management to avoid double writes, but it still suffered from the overhead of journaling in the underlying file system. Eventually, BlueStore bypassed the file system to achieve efficient transactions. So this graph compares the performance of BlueStore and FileStore on XFS for transactional object writes. In this benchmark, a client writes different sized objects using queue depth of 128 to a 16-node Ceph cluster with hard disk drives. The x-axis is the object size, which ranges from 64 kilobytes to 1 megabyte, and the y-axis is the throughput in megabytes per second. As you can see, the throughput of BlueStore is 2 times higher for larger I/O sizes than FileStore. There are multiple optimizations in play here, but most of the speedup in BlueStore stems from avoiding double writes. Also, you can see that BlueStore has significantly lower variance than FileStore because it has a better control over writes, which brings us to the next challenge, controlling writes. So the operating system page cache uses a write-back caching policy where data write is acknowledged immediately once it's in the OS memory. Data is then asynchronously written to disk. This is great for interactive users because it results in a responsive system, but for I/O-heavy systems, this policy quickly leads to the accumulation of many dirty pages. Since there's no fine-grained control over when the write-back of these dirty pages happen, the write back ends up interfering with the foreground writes, which leads to high latency. Calling sync helps with bounding the amount of dirty data pages, but there's no control over the write back of metadata pages that are written to the journal as a result of calling sync. And on a system with millions of directories and files, the write back of random metadata results in many random writes, which interferes with the foreground writes and increases tail latency. BlueStore also implements a cache, but it uses a write-through policy. With write-through policy, data is immediately written to disk, and it's only acknowledged after it was written. Therefore, there's no pending stream of writes to interfere with the foreground writes. And in case you wonder that a write-through would increase the write latency, I'll just remind you that with FileStore, with the user space write-ahead log file, FileStore was already paying the cost of a write because after writing data to the log, it was calling fsig to commit the transaction. So this graph compares the 95th and above percentile tail latencies of BlueStore and FileStore for transactional object writes. The setup is the same as before, a single client writing objects using queue depth of 128 to a 16-node Ceph cluster using hard drives. The x-axis is the latency in log scale, and the y-axis is the percentile. The left two blue lines are for BlueStore with 64 kilobyte and 1 megabyte object writes, and the right two red lines for FileStore with similar sized object writes. As you can see, the high percentiles of tail latency in BlueStore is an order of magnitude lower than FileStore. Another big challenge for file system-based backends is supporting new and backward incompatible hardware. A new class of data center drives are emerging with the attractive features but a backward incompatible zone interface. The zone interface divides the LBA space into sequence of large zones. Each zone is several hundred megabytes in size and must be written sequentially from beginning to the end. Therefore, random writes and overwrites of small data is not possible. Hard drives with the zone interface internally use what is known as shingled magnetic recording, which increases their capacity by 20% or more over conventional drives with the block interface. And more recently, zoned namespace SSDs expose NAND flash erase blocks as zones, eliminating garbage collection and reducing tail I/O latency. The zone interface requires a log structured or copy-on-write data management, but most production file systems, on the other hand, are overwrite file systems. They need fundamental changes to adopt these devices. Therefore, it's not clear if they will ever adopt these new devices. In BlueStore, on the other hand, we have a direct access to the device, and we have already successfully completed storing metadata on zone devices in a short period of time. And now we're working on storing data on zone devices as well. So there are other important challenges that you can read about in the paper. Being a clean slate backend, BlueStore avoids most of these challenges by design. It is implemented entirely in user space and runs on a raw disk. It uses direct I/O and in-kernel asynchronous libAIO framework for reading and writing the disk. All of the metadata, including low-level metadata such as extent bitmap, are stored in RuxDB, a key value database. And RuxDB runs on a minimal user space file system called BlueFS, which just implements a handful of system calls that are needed by RuxDB. Large data writes and overwrites of data are done to the disk directly using copy on write. Small writes are batched in RuxDB and then written asynchronously to increase the I/O efficiency. So you can find the more details of BlueStore in the paper. Although BlueStore performs better than file system-based backends, it's just the first step towards an efficient storage backend. There are many important challenges ahead. For example, although RuxDB improves the metadata performance significantly, its compaction overhead has become the new bottleneck. Another example is with the new high-end NVMe SSDs, the I/O bound workloads are now becoming disk bound, CPU bound because the I/O latency is dropping. Addressing these challenges requires further research and optimizations. So in conclusion, distributed storage systems conventionally adopt file systems as the storage backend and then keep working around the limitations of file systems. This results in a significant accidental complexity and performance loss. Perhaps the biggest reason that holds developers back from building a custom backend is that building a custom backend is the belief that it will take many years to complete a custom backend. The Ceph team spent about 8 years wrestling with different file systems to achieve good performance, but it took them less than 2 years to build a custom backend from scratch, which outperformed all of the previous backends and also enabled many new features. So the takeaway for the designers of distributed storage systems is that stop trying to fit general purpose file systems to your needs and implement a custom backend. It is becoming especially important as we're moving to the era of fast and backward incompatible storage devices. That concludes my talk, and I can now take questions.
Noman Rafiq from Google, that's a great talk. I was wondering if anybody in Ceph tried to talk to people who work on this kernel file system and tried to see if...
I can't hear your question.
Noman Rafiq from Google.
Okay.
Can you hear me now?
Yeah.
Okay. I was wondering if anybody from Ceph talked to people who work on kernel file systems to try to see if they could do something to better support the use case they had.
Yeah, actually, evolution of Ceph happened in together with the kernel developers. Like actually, Ceph ended up adding a few new system calls to Linux, which you can read about in the paper. And basically, all the path that took Ceph to current stage was done with very knowledgeable people that were doing this work.
Hi, this is Sulbhi Palande from University of British Columbia. I assume your BlueFS is log structured to support host-managed SMR drives.
Yes.
I was wondering what is your tail latency for how do you avoid the bad garbage collection performance?
Yeah, so BlueFS is only supports running RuxDB, and RuxDB generates this large SSD files, which are large files that you can map directly to the zones. So there's basically no overhead of running RuxDB on host-managed SMR drives. And the data part, we've just started working on that.
Okay, thank you.
Yeah.
So Ethan Miller, UC Santa Cruz, I kind of know a little bit about the early history there.
Yeah.
So the question is, if you look at EBOFs originally, right, you switched away from it 2 years later. The question is, why won't this happen again with what you're doing now? In other words, they switched away, and if they had just stuck with it, it would have matured and everything else. Why won't this happen again?
So I think with EBOFs, it was a very a prototype kind of file system, and it didn't have a bunch of features that they needed. But with BlueStore, the Ceph team is now ahead of file systems in terms of features. So, and also, as I said, the biggest challenge is adopting new hardware. So, yeah, I don't see current file systems adopting the backward incompatible hardware. There have been some attempts that failed, so that's unlikely to happen. So that's why.
Thanks.
Yep.
Let's have one last question.
Good work.
Thank you.
Reza Doc, Stony Brook University. So you say it took 2 years to stabilize the work.
Yeah.
And yet we see more and more papers here and elsewhere that find new creative ways to find bugs in system software and file systems. So how have you run it through any of these more advanced techniques to see how truly high quality the code is, or next year is going to be a paper about all the bugs that got found and fixed in BlueStore?
Okay, so we do it empirically, which means 70% of Ceph customers that switch to BlueStore, and they've started to store petabytes of data on that. So that's how we say it's stable. It's not like it's a prototype, we just completed this. Probably most of Ceph, it was 70 years in 2018, it's probably much higher. I mean 70% in 2018, it's probably much higher than that. People are using it in production for storing real data.
Okay. All right. Thank you.
Yep.
Right, let's thank the speaker again.